Hello mga ka-tribes! Welcome to Daddy Brew TV. This is your host, the adventurous math teacher. So for today's video, let's discuss part 2 of lesson 2, quarter 4, the central limit theorem without replacement. In part 1 of our discussions about the central limit theorem with replacement, we concluded that if samples of size n is sufficiently large, are drawn from any population with a mean and standard deviation, then the sampling distribution of sample means approximates a normal curve or normal distribution. What if we will consider the same population problem and a sample of size 2 can be drawn without replacement? Thus, the sampling distribution of sample means approximates also a normal distribution. To find the answer, let us consider example number 2. Consider the same population consisting of the values 1, 2, 3, and 4. This time, consider all possible samples of size 2 that can be drawn without replacement. Now, let us discuss this table. As you can see, there are 12 observations. Why? Because the samples are drawn without replacement. So what are these samples? We have 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, 4, 3. Okay, now we are now ready to determine the sample mean of the samples. Now, to do this, again, let's add 1 and 2 and divided by 2, the quotient is 1.5. 1 plus 3 divided by 2 equal to 2.0. 1 plus 4 divided by 2 equal to 2.5. 2 plus 1 divided by 2 is equal to 1.5. 2 plus 3 divided by 2 is equal to 2.5. 2 plus 4 divided by 2 is equal to 3.0. 3 plus 1 divided by 2 is 2.0. 3 plus 2 divided by 2 is 2.5. 3 plus 4 divided by 2 is 3.5. 4 plus 1 divided by 2 is 2.5. 4 plus 2 divided by 2 is 3.0. And 4 plus 3 divided by 2 is 3.5. Okay. Let's determine now the summation of all the sample means. When we add all the samples, the result is 30. And this 30 is the summation of the sample mean. Since the summation of the sample mean is equal to 30, we are now ready to solve or calculate the mean of the sampling distribution of means. Using the formula, mu sub x bar is equal now to the summation of the sample mean over small n. So what is the summation of the sample mean? 30. So let's replace it by 30 divided by the number of observations, that is equal to 12. And therefore, 30 divided by 12 is 2.5. So, as you notice, the mean of this population is 2.5, same as the mean when the sample is drawn with replacement. To calculate the variance of the sampling distribution of means, let's continue working on our table. Now, of course, you have to subtract again the sample mean to the obtained mean of the sampling distribution of means, which is 2.5. So 1.5 minus 2.5, that is negative 1.0. 2.0 minus 2.5 is equal to negative 0.5. 2.5 minus 2.5 is equal to 0. 1.5 minus 2.5 is equal to negative 1.0. 2.5 minus 2.5 is equal to 0. 3.0 minus 2.5 is equal to positive 0.5. 2.0 minus 2.5 is equal to negative 0.5. 2.5 minus 2.5 is equal to 0. 3.5 minus 2.5 is equal to 1.0. 2.5 minus 2.5 is equal to 0. 3.0 minus 2.5 is equal to 0.5. And 3.5 minus 2.5 is 1.0. Then, let's square the difference. That is, negative 1 squared is equal to 1.0. Negative 0.5 squared is equal to 0.25. Square of 0 is 0. The square of negative 1 is positive 1.0. The square of 0 is also 0. The square of zero point 0.5 is positive 0.25. The square of negative zero point 0.5 is positive 0.25. The square of 0 is 0. The square of 1 is 1.02. Or also, 0 or square of 0 is 0. Zero point 0.5 squared is 0.25 and 1.0 is equal to positive 1.0 when you square it. And getting the summation now of the square of the difference deviation is equal to 5.0. Now, we are now ready to calculate the variance of the sampling distribution of means. Using the formula, sigma squared sub x bar is equal now to the summation of the quantity x bar minus mu sub x bar quantity squared over small n. Now, the summation of x bar minus the mu sub x bar squared is equal to 5 divided by n, where n is equal to 12. And that is now equal to 0.42 or 42 hundredths. And that is now the variance of the sampling distribution of the means. Of course, to determine the standard deviation, just simply extract the square root of the variance, which is now equal to the summation of x bar minus mu sub x bar squared over n, wherein the variance is equal to 0.42, and extract 0.42, that is now equal to 0.65, and this one is the standard deviation of the sampling distribution of means. Before we construct the probability histogram, let us determine first the frequency of our sample means. Now, for a sample mean of 1.5, there are two frequencies. For a sample mean of 2.0, there are also two frequencies. For a sample mean of 2.5, there are 4. For a sample mean of 3.0, there are 2. And for a sample mean of 3.5, there are 2 also. We can now define the probability of the sample mean given its frequencies. Okay, for a sample mean of 1.5, the probability is 2 over 12. A sample mean of 2.0, that is 2 over 12 also. A sample mean of 2.5, that is 4 over 12. A sample mean of 3.0, that is 2 over 12. And a sample mean of 3.5 is 2 over 12. So, to illustrate the probability histogram of the sampling distribution of means without replacement, where n is equal to 2, let the horizontal axis be the sample means and the vertical axis be the probability of the means. As you notice, the sampling distribution of means does not approximate the normal distribution, unlike when the samples are selected with replacement. So, let's conclude that the sampling distribution of the sample means taken with replacement from a population with population mean and variance will approach a normal distribution according to the central limit theorem. Let's sum up our discussions. What was learned in our part 1 lesson about sampling with replacement is summarized in the central limit theorem as follows. 1. As the sample size n increases, the sampling distribution of the means approaches a normal distribution. 2. The mean of the sampling distribution of means is equal to the mean of the population. 3. The variance of the sampling distribution of means is equal to the variance of the population divided by the sample size n. And 4. The standard deviation of the sampling distribution of means is equal to the standard deviation of the population divided by the square root of the sample size n. Before I end this video, let me share to you this FYI. The French-born mathematician Abraham de Moivre from 1667 to 1754 proved the first version of the central limit theorem. He used the normal distribution to approximate the distribution of the number of heads that will result when a fair coin is tossed a large number of times. But it was the Russian mathematician, mechanician, and physicist Alexander Lyapunov from 1857 to 1918 who gave the first rigorous proof of the general central limit theorem. So that's the end of our discussion about central limit theorem. See you on my next video. Bye.